model to make accurate predictions about the flow and about performance. But there is presently available no theory that will predict the transition, that is, this whole line. Higher up on the chart, in the other regions, the theories are not as complete, and there is no theory that will predict this line or the hysteresis region either. We might summarize all this as follows. When we first begin to study a problem in fluid mechanics, we may not even know the gross flow patterns to expect. After we've accumulated enough systematic information, in visual form or by other means, we can correlate the data, as for example on the chart. Finally, we can use the flow models so found as the basis for mathematical models, and if these are successful, we can then make paper and pencil predictions about a good many details. We can do that in this regime on the diffuser chart. The information inherent in the second or correlation stage is often useful for other purposes. Sometimes it tells us how to locate optimums, and sometimes it suggests improved designs. In the diffuser example, the lowest line in fact tells us the geometries that give maximum pressure rise for a fixed length of diffuser. The chart itself also suggests a way to improve short diffusers. Short diffusers usually mean wide angles, but wide angles mean separation, poor patterns, and poor performance. The chart suggests that perhaps what we ought to do is to divide up the passages into smaller passages, each one of which does not cross the first line of stall either this way or this way. Let's see if this idea works. Here you see a fully developed stall in a diffuser with a divergence angle of about 45 degrees. Let's insert an assembly of vanes designed so that each passage lies below the line of first appreciable separation on our flow regime chart. When the vanes are removed, the stall comes back. It's often useful to use more than one method of visualization. Let's use another technique to look at some of the things we've seen before, and also to study a new pattern of flow regimes, laminar turbulent transition. For this purpose, a useful but very simple method is dye injection. All you need is a flask of adjustable height and a manifold with hypodermic injectors. Any dye can be used provided its density is very close to that of the working fluid. Here you see the jet flow pattern made visible with streak lines of dye. Compare the pattern of the jet flow you see here with the bubble picture we saw earlier. The recirculating eddies, which you now see at the sides of the main flow, are made visible by seeping dye through holes in each wall. Dye must be injected with some care. If we apply the wrong pressure to the injectors, the dye will come out too fast or too slow. This causes jet instability, as you see here. Here's an apparatus to look at the flow very near the wall. The apparatus consists of a dye reservoir connected through a thin rectangular slit to the flow. The slit is only a few mils wide. The layers of flow extremely close to the wall are crucial in heat and mass transfer, in flow separation, and in the structure of the turbulent shear layer. The dye is turned on and seeps slowly through the slit. It moves upstream because the diffuser walls are at a very large angle and the flow is stalled. The walls are moved parallel. Now we are looking directly at the wall which contains the slit. The slit is near the left edge of the picture. Notice the smooth, almost glass-like appearance of the dye. This is typical of a laminar boundary layer. Now we introduce effective trips. The flow over the regular, streaky structure you see is typical of the wall layers of the turbulent boundary layer. The dye streaks are actually zones of low-speed flow, and the clear areas in between are faster-moving fluid. If we remove one of the trips, we can observe the transition region between laminar and turbulent flow over the slit. In this region, you can see laminar flow side by side with turbulent flow. You can also see transient spots of turbulence moving down through the flow. If we move the remaining trip further upstream, the fraction of the flow which is turbulent at the slit decreases. Finally, the entire flow becomes laminar again. In the laminar turbulent transition problem, we again find several patterns of flow, and again the state of knowledge is different for each pattern. If we know the flow is laminar, we can calculate many fine details of performance from well-developed theory. If we know the flow is turbulent, we have workable approximate theories for a few simple cases. In a number of other cases, we also have good data correlations for such things as friction and heat transfer coefficients. If the flow is in the transition region, the theory is quite incomplete. As in our diffuser example, theoretical prediction of when a shift will occur from one regime to another is the most difficult thing of all. We have only part of the theory for a handful of cases and data correlations for a few more. We can predict results based on established flow models, but even in this very old and much studied problem, we still need correlations of data to predict the flow pattern that will actually occur. Let's consider one more example. Here's a flat plate